Hello and welcome. This is Ron, VK2DQ. You're doing the standard amateur radio course with the Radio and Electronics School. This tutorial is on propagation, tutorial 25, and your self-test software for this tutorial is drill number 19. Do your best to try and get a score in the vicinity of 90% in the drills. When you're getting around about 90% in most of the drills, then you're ready to do your theory assessment. This slide is a diagram of the Earth's atmosphere. As you probably know, in these tutorials I do give you a little bit of background information and additional material that, strictly speaking, you aren't examined on in the syllabus. But you need to know these things to make it easier for you to understand the answers to the questions that you do need to know. The real test of your readiness for the examination is not the tutorials, it's your performance in the drill software. Now, what we have here is a cross-section of the Earth's atmosphere, and the purpose of me showing you this is just to show you the heights of the different ionospheric layers. Radio waves travel in straight lines. All radio waves travel in straight lines except very low frequency radio waves, and with them, you know, in 1 or 2 megahertz and lower, you can get a substantial ground wave. But most long distance radio communication relies on radio waves being refracted from the ionosphere, and the ionosphere is a part of the atmosphere, and the layers of the ionosphere are charged because ultraviolet and other radiation from the sun strips away electrons from the gases in the atmosphere. This leaves a region around the Earth, or particularly on the sunny side of the Earth, where there is a charged layer of gas or ionized gas, and these regions of ionized gas make up the ionospheric layers. Different layers appear and disappear at different times of day because the sun is the primary cause of ionization in our upper atmosphere. The ionospheric layers are, broadly speaking, broken up into 4 different altitudes. I have to say broadly speaking because the actual height of an ionospheric layer is not a specific height, because they're bands and their actual altitude can change depending on the degree of ionization from the sun. The greater the amount of sunshine and ultraviolet radiation, the more ionized the different layers of the ionosphere become. We need these layers as radio amateurs because they are able to refract, not reflect, they are able to refract our signal back to Earth. If it wasn't for them, our radio signal, because the Earth is round, our radio signal would just leave the Earth and go into space and never come back. So if we want to communicate on HF particularly around the world, then we rely on refraction from these ionospheric layers to bring our signal back to Earth. When it comes back to Earth, it is reflected from the Earth, and it may go back again to the layer and be refracted again, and that can happen several times, and your signal can travel from one part of the Earth to the other by being refracted from the ionosphere and reflected from the Earth's surface, and that's called a hop. And there could be multiple hops in your communication with an overseas station. Let's have a look at roughly at the heights of the layers. The lowest layer is the D layer, and this slide puts a little bit in perspective. How high is the D layer? It's about 70 kilometres, and that's higher than the highest clouds. It's higher than jet aircraft. It's higher than any mountain. It's higher than the highest weather balloon. It's 70 kilometres high. The D layer only exists through the day. Because the D layer is way down low in the atmosphere, the density of the air molecules is fairly high there, and so it takes an awful lot of the sun's energy to ionize the D region. So the D region normally appears at early morning, and it's gone not long after the sun sets. The D layer through the day will absorb most frequencies up to about 3 megahertz. If you wanted to communicate on the 80 meter band through the day, you could, because the 80 meter band is just high enough to penetrate the D layer and enable you to refract your signal off either the F1 or F2 during the daytime. But when the night arrives, when the sun sets, probably half an hour, 40 minutes after the sun sets, the D region is gone. Have you ever been driving in a motor vehicle listening to AM radio late afternoon, and you're probably, as you're travelling on your journey, you have to tune to different local stations? This is through the day, and on your trip suddenly the sun goes down, and within about half an hour on your car radio you're hearing signals from all over Australia. You might be in Broken Hill and you're hearing radio stations from Brisbane. And the reason for that is their frequency is in the order of 500 to 1500 kilohertz roughly, and those AM stations are unable to penetrate the D layer through the day. It absorbs them. The wave goes into them and it absorbs all of their energy. But once the sun goes down, 40 minutes later, the D layer is gone, and suddenly there is all this radio reception of broadcast band AM radio all over Australia. The E layer, it's probably about 120 kilometres here on this diagram. The E layer is not very reliable. It comes and goes. It's not always there. When it is there, it's particularly good for 6 metre propagation. And because the E layer is sporadic, that 6 metre propagation is called sporadic E. The layers that are most important to us are the F1, and the F1's just over 200 kilometres high, and the F2, which is 450, 460 kilometres high. During the day, we have an F2, which is the highest layer, and an F1. We have two distinct layers because of the degree of ionisation through the day is higher. At night time, the F1 and F2 merge. They combine together to form the F layer. So through the day, you have D, E, F1 and F2 always, and E is on and off. It's quite sporadic, but you always have an F1, F2 and F1, and you always have a D through the day. At night time, you're unlikely to have an E layer at all. You won't have a D layer at all, and the F1 and the F2 merge, and we just call it the F layer. These layers are crucial for radio amateurs for long distance communications. You'll notice that between the F1 and the F2 there is meteor showers. Meteors are not uncommon. There are thousands of micrometeors that hit the Earth's surface every day. And, sorry, not hit the Earth's surface, but hits the Earth's surface. It's called a meteorite. There are thousands of meteors hit the Earth's atmosphere every day. These meteor storms are predictable, and they can even be looked up in an almanac. And meteors will also ionize the atmosphere and cause the layers to increase in their ionization. This is a good diagram to have on your wall, I think. The ionosphere is here. And if you wanted to, you could screen grab this or use a screen capture program or the clipping tool in Windows 7 and you could print this because it's a very, very handy reference. And if I remember to do it, and I probably will, I'll put a PDF of this image in your document folder. Because the sun is the major contributor to ionisation of the upper atmosphere, we need, as radio amateurs, to have a little bit deeper knowledge of just how the sun does affect the ionosphere over time. Certainly at night time there's not going to be as much ionisation as there is through the day. The slide on screen is a graph of what is known as the 11-year sunspot cycle, because the degree of ionisation of the atmosphere is dependent upon the number of sunspots on the sun. The sunspot on the sun is an area on the sun that looks like a dark spot. It only looks like a dark spot because it's a lot cooler than the surrounding sun. Sunspots are extremely hot, but they appear dark because the surrounding sun is much hotter than them. Sunspots are thought to be the exit point of solar flares or flux ropes. A flux rope can go in and out of a couple of sunspots, and for a long time now mankind has been looking at the number of sunspots on the sun, counting them, recording them, and the degree of ionisation of the ionosphere has been found to vary over an 11-year cycle, because over 11 years the sun becomes spottier and spottier and spottier, reaches a maximum spottiness, and that gives us maximum ionisation, and then it slowly falls off to the least amount of spottiness, and then 11 years later it reaches maximum spottiness again. Maximum sunspot number means maximum ionisation, and that means the best long-distance communication. So radio amateurs, watch out for this 11-year sunspot cycle, because they know when the sunspots are high, they can communicate with just about anyone, anywhere on Earth, with minimal amount of power. Here's the last sunspot cycle. On the bottom axes, the x-axis, we've got the year. So the peak of the last sunspot cycle was around about here, about just before 2001. That was the peak, and we reached maximum spottiness then, and during that time radio communication was absolutely fantastic. Doesn't mean it's not fantastic at other times, it just means that you have to use a lower frequency, because when the ionosphere is highly ionized, it is able to refract high frequencies easier. So 28 megahertz, for example, will only be refracted when there's a high degree of ionisation. But during low sunspot activity, or during a time when the ionosphere is not very charged, all radio amateurs do is move downwards in frequency till they meet a frequency that will be refracted from the ionosphere. At the moment we're around about here. So this is the prediction. This is the variation, possible variation in the prediction, but this is the prediction here. So you can see that we're well on our way at the moment to reaching a predicted peak in sunspot activity around about, what's that? 2013, about 2013, maybe the end of 2012, we're expecting a sunspot peak, and then it drops off again. That's the 11-year sunspot cycle, and that's the primary contributing factor to the amount of ionisation that our sun does to our ionosphere. You need to know some definitions of different types of waves, and this slide will help us with that. Here we've got a radio transmitter, it's a transmitting antenna, And you'll see that for a short distance from the antenna, depending on the frequency, there is a ground wave. And a ground wave is a wave that follows the surface of the ground. So if there are hills here, ground waves are a low enough frequency to actually fold themselves over those hills and give you good communications without reliance on the ionosphere. Ground waves have nothing to do with the ionosphere. Ground waves really only exist at very low frequencies. At VHF, for example, there is no ground wave. You might think there's a ground wave if you're talking to a radio amateur 10 kilometres away on VHF. You might think that you're communicating with him via ground wave, but you're actually using this wave, which is not using the ionosphere. It's just a wave that's going straight from the aerial, straight from your antenna, straight to the other radio amateur's antenna, and that is called a direct wave, and it doesn't rely on ionospheric communications. Direct wave. Most of the time when you're communicating above 3 megahertz, you're communicating, if you're talking to a local, you're communicating on direct wave. Or you could possibly, if you're low enough in frequency, be communicating with him on ground wave. But those two, direct wave and ground wave, do not rely on the ionosphere at all. That we've just drawn the ionosphere as one layer here. Well, let's just call it the F layer. Let's just say it's a single layer for the time being to make it easier. A wave that leaves the antenna and enters an ionospheric layer and returns to Earth to be received is called a skywave. You need to know that. All waves that are refracted off the ionosphere are called skywaves. If the frequency is too high, then refraction won't occur. This is not a particularly good diagram here because this skywave looks like it's reflecting off that ionospheric layer when in fact what really happens, the wave enters the ionosphere and begins to be slowly bent. And if it's bent enough, it will return to Earth. And of course, it will be reflected from the Earth, and it might be refracted again from the ionosphere once more, if you can imagine the ionosphere continuing around like that. If the frequency of the transmission is too high, then the wave will enter the ionosphere, start to bend, but not bend enough and be lost and go out to space. That's because this frequency is above the maximum usable frequency. The maximum usable frequency is the highest frequency that will be refracted from the ionosphere. So if the IPS, the Ionospheric Prediction Service, says the highest frequency, the MUF is 20 megahertz for a particular time of day and place, then the radio amateur knows that in order to communicate overseas, he's going to have to use a much lower frequency than 20 megahertz. In fact, the best frequency to use is the optimum working frequency, and the optimum working frequency is about 15% lower than the MUF. So it's a little bit lower than the MUF, and because it wouldn't be wise to transmit exactly on the MUF, because you might find that 1 minute your signal's escaping from the ionosphere, next moment your signal's being refracted. So operating at the maximum usable frequency is not wise, and so a little bit down from the maximum usable frequency is the optimum working frequency, and that's what you should be on. So I'm going to clear this diagram and come back and explain a couple of other terms to you. The distance from the transmitter the distance between the transmitter and where a sky wave first returns to Earth, and that's this one here. So the distance from the transmitter to where the sky wave first returns to Earth, the first hop, is called the skip distance. The higher the frequency, the longer that skip distance will be. On 80 metres, the skip distance is very short. On 10 metres, the skip distance is much longer. The skip distance is also affected by the height of the ionosphere. If the layer was lower, then the skip distance would be shorter. If the layer was higher, then the skip distance would be longer, and so on. So the skip distance then is the distance from the transmitter to where the sky wave first returns to Earth, that distance there. The area between the end of the ground wave is here, and to where the sky wave first returns to Earth is called the skip zone. You're highly likely to get questions about skip distance and skip zone. The skip zone, if there was a station here, that's an antenna by the way, I know I'm not the greatest drawer, but if there was an amateur station here, he would not receive this station because he's too far away to receive him on ground wave, he's too far away to receive him on direct wave, and the sky wave is going over the top of him. So the skip zone is a no signal area. You need to remember skip zone and skip distance. There are other things that determine our ability to communicate from the ionosphere, and one of those is the angle of radiation. That's the angle that our wave leaves the antenna. That angle can be measured between the ionosphere and our wave, or it can be measured between our wave and the ground. But if our antenna has a high angle of radiation, this is a high angle of radiation, then it is in the ionosphere for a less amount of time, and if we're lucky, it'll be bent and return to Earth. But the chances are a high angle of radiation will cause the wave to go to space. A low angle of radiation, on the other hand, means that we glance the atmosphere, much like glancing the surface of a pond with a stone, and the wave is refracted. The process at the ionosphere is refraction, not reflection, because reflection occurs from a sharp boundary. So that is refraction. A wave is reflected from the Earth because the wave hits the Earth. The Earth is a conductor. The wave hits the Earth and immediately is reflected off, whereas refraction is a slow bending, and if that slow bending isn't fast enough, our wave escapes to space. If there's enough bending, or our frequency is low enough, there will be refraction and our wave will return to Earth. Here's another diagram indicating the possibilities that can occur during ionospheric communications, long distance HF communications via the ionosphere. Here we've got an E layer. An E layer is not very reliable, but if we did have an E layer, the skip distance would be fairly short because the E layer is only about 70 kilometres. And we're showing the F2 here, but it could just as easily be the F1 or F2 or F1 plus F2. And obviously, if a radio amateur is going to communicate, this is the Earth, and if the Sun is here, the good old Sun, then on this side of the Earth there's going to be an F1 an F2, maybe an E, and a D layer, because that's getting maximum sunlight. But on the other side of the Earth, what's going to happen at sunset about here, say, the D layer is going to fizzle out and disappear because there's no radiation there, and the F1 and F2 are going to merge into the F layer. So primarily, and that F layer is going to go right round. And then it'll split again because it's getting sunlight and merge into F1 and F2. The other thing that can happen, which we're not too happy about as radio amateurs, is it's possible for a wave, let's say the receiver is here. This wave is travelling from the transmitting station, being refracted from the ionosphere and being received. It's possible for a bit of the wave to be refracted by a different portion of the layer and also be received. But the problem is here that these two waves have travelled a different distance. So if they arrive at the receiver in phase, then the receiving station will get a stronger signal. But what will happen not too long after that, their phase will change, they will arrive at the receiver out of phase, and the signal strength will just drop almost to nothing, or it could even disappear. That's multiple path reception, and that's called multiple path fading. That's one of the primary causes of the signal fading in and out on HF radio bands when you're using ionospheric communications. There's a couple of things you need to know about the waves themselves, about electromagnetic waves. Electromagnetic waves are just light at a different frequency. The electromagnetic spectrum is huge, and radio waves, light waves, microwaves, all waves, they're all electromagnetic waves, and the only difference is their frequency. The wave that comes out of your antenna is no different than the beam of light that comes from a torch. All electromagnetic waves, they're called electromagnetic because an electromagnetic wave comprises of a magnetic field and electric field. And the magnetic field and electric field are at right angles to each other. A bit hard to draw, and we don't have to draw a complex diagram. Generally speaking, if this is a vertical antenna, generally speaking, if you have a vertical antenna, the waves, the electric field that antenna radiates will be vertical. That's the electric field. So the electric field is vertical if you have a vertical antenna. And the magnetic field of the wave is horizontal. Why this is important to us is we need to know how a wave is polarized. And it's common practice for people to say if you have a vertical antenna, you have vertical polarization. And if you have a horizontal antenna, you have a horizontal polarization. Well, that's wrong. Polarization is determined by the direction of the electric field, not the magnetic field. If the electric field is vertical, then the polarization is vertical. If the electric field is horizontal, then the polarization is horizontal. Well, you might say, well, okay, if I've got a vertical antenna, then I've got vertical polarization. Not so. When you're communicating via the ionosphere, it doesn't matter whether you're using a horizontal or vertically polarized antenna. When that wave refracts from the ionosphere, the polarization will twist. Vertical polarization could become horizontal polarization. And this is why radio amateurs can talk when they have different antennas. Someone has a vertical antenna, someone has a horizontal antenna. They're communicating by the ionosphere, and it works because there is a twisting of the polarization. The important thing is this: it is for this reason we never use the antenna to describe the polarization. We never say we have a vertical antenna, therefore we're vertically polarized. Polarization is determined only by the direction of the electric field in the wave. So if the electric field in the wave is vertical, irrespective of the type of antenna that wave come from, that is vertical polarization. Likewise, if the electric field is horizontal, that is horizontal polarization. Always refer to the wave to determine the polarization and its electric field, not the antenna. The other thing you need to know is the velocity of an electromagnetic wave. Now, all electromagnetic waves travel at the same velocity, and that's 300 million meters per second. That's very, very fast. That's probably, roughly speaking, that's around the Earth 12 times in a second. 300 million meters per second. What you have to be careful of, you're very likely to be asked the velocity of an electromagnetic wave. Speed of light, 300 million meters per second, but they can do tricky things. For example, they could say 300,000 kilometers per second. So in the drills, I'll be giving you different ways in which this figure of 300 million meters per second can appear in the assessment. Well, the syllabus for the standard is fairly lightly covers propagation, so I'm not going to talk to you and waffle much longer. I thought I'd bring up this slide of the electromagnetic spectrum so that you could just have a look at it. What I'm going to be doing now is just going through your drill questions on propagation, because there aren't a lot. There's a lot more to learn about propagation than what I've given you here, but there's no more to learn to the best of my knowledge. And if I pick something up in the question sets, there's no more, I'll cover it, but there's no more to need to know for the standard license and what we've just covered. And if I've made a blue, I'll cover it when I do the sample questions with you next. But have a good look at this slide here. You might want to pause the video and have a good look at the slide, because it gives you the wavelength of the spectrum. So 10 to the power 1 would be 10 meters. That's the 28 megahertz amateur radio band. And on this scale here, you have the frequency. And the higher radio waves become, the more energetic they become. So way up here we've got gamma rays, X-rays, soft X-rays, ultraviolet, infrared, microwaves, radio waves. All of those are electromagnetic waves. They're all the same. The only difference between them is the frequency. How about we look at our question sets, and I'll see if we've covered it all, because I don't want to drag this course out any longer than it has to be for you. I've only got a few questions to go through with you on propagation, and you'll notice that quite often the questions are repeated, which should tell you something about the importance that you should know them. If you see questions of the same type, then a very high probability that you're going to be asked one of those questions in assessment. 19.1. The term vertically polarized electromagnetic wave refers to a wave in which the electric field oscillates vertically. Never forget this. The polarization of an electromagnetic wave is only determined by the direction of the electric field in the wave. It has nothing to do with the antenna. The magnetic field is at right angles to the electric field. So if the electric field is vertical, the magnetic field is horizontal. The wave polarization gets its name only from the direction of the electric field. Question 19.2. The absorption of radio waves by the ionosphere depends on their frequency. Higher frequency waves can penetrate the ionosphere and have little absorption. Low frequency waves, particularly those below 3 megahertz, are nearly always totally absorbed by the D layer. 19.3. Ionization in the ionosphere is caused primarily by ultraviolet and other rotation, goodness me, I saw this, ultraviolet and other radiation from the sun. If you answer that, rotation of the moon, I don't know, someone had a sense of humour to stick that one in. I think it might have been me. So ionisation is primarily caused by ultraviolet and other radiation from the sun. 19.4. The bending or refraction of high-frequency radio waves in the ionosphere becomes greater as the frequency is increased? No. Remains the same regardless of frequency? No. Becomes less as the frequency is increased. So the higher the frequency, the less the amount of bending, and the more likelihood that your wave won't even return to Earth. So frequency is very important. 19.5. RF waves travelling in free space travel at a speed of 300 million metres per second. Well, I think that's 10 to the power 9. I think it's this one here. See the 10 to the power 9? What that means is you type a 3, and the decimal point is there if we had one. I'm putting it in and then taking it out. And now we have to add 9 zeros. 1, 2, 3, 4, 5, 5, 6, 7, 8. No, that's not going to work. Yes, it is. It is right. 1, 2, 3, 4, 5, 6, 7, 8. No, that's not. That's 3 to 10 to the power 8. That's wrong. Oops. It's this one here. I'll just fix that up. It's 300 by 10 to the power 6, because if we write 300 and then 10 to the power 6 means add 6 zeros, 1, 2, 3, 1, 2, 3 meters per second. So the answer is 300 by 10 to the power 6. And we're going to do a couple more of those because you're bound to get one. 19.6. Radio frequency waves travelling in free space travel at a speed of, let's have a look now. Well, they're not, no, 300 kilometres per second is the same as 300 million metres per second. 19.7. In space, radio waves travel at approximately 300 million metres per second. So with those three questions, you're seeing three possible ways that they can give you that number of the speed of electromagnetic radiation, or most people call it the speed of light. Don't get stuck, don't get caught with that. Make sure you are aware that 300 kilometres per second is the same as 300 million metres per second, and that's the same as 300 by 10 to the power 6. Question 19.8. Long-distance high-frequency communication at night is normally via the ionospheric. Well, at night time, the D layer is gone, so's the E, and the F1 and F2, the F2 being the highest, merge to form the F layer. So nighttime communications is generally, nearly always, via the F layer. At night, the ionosphere, this is 19.9, at night the ionosphere normally consists of an F layer. You may get D and E through the day. You may get E and F. You will get D through the day, and you will get F, but E is rather sporadic. So nighttime, you've just got the F layer. 19.10. In the propagation diagram below, the question mark is what? The question mark is going from the end of the ground wave to where the sky wave first returns to Earth. So this would be a no signal area unless we had a sky wave coming in. If this was our signal, we wouldn't be able to communicate with anyone in there because our ground wave is not reaching them and our sky wave is going over the top and our direct wave is too far away. So that is called the skip zone. The question mark is the skip zone. 1911, communications over 500 kilometres on the 80 metre band at night depend primarily on sky wave propagation. 19 19.12, transmission of high-frequency signals over distances is generally due to skywave propagation. You're getting the picture of how important it might be to know what skywave propagation is. 19.13, a radio wave which travels to a receiver via the ionosphere is called a skywave. 19.14, skywave communication between amateur stations is not possible above the maximum usable frequency. If you operate above the maximum usable frequency, your wave won't refract from the ionosphere, it will penetrate it and escape into space. (19.15) The highest frequency which may be employed in given circumstances for communication between two given stations is the maximum usable frequency, the MUF. 19.16, the main advantage of ground wave propagation is that, well, it doesn't rely on the ionosphere. Have we got that? It is not affected by ionospheric disturbances. Ground waves have nothing to do with the ionosphere. Neither do direct waves. They go directly from one antenna to another and have nothing to do with the ionosphere. 19.7, a decrease in the height of the ionosphere will cause the skip distance to decrease. If the layer is lower, it will bounce back or refract back sooner, I should say. 19.18, the same question but the opposite way around. An increase in the height of the ionosphere will cause the skip distance to increase. The more charged the ionosphere, the higher it is and the greater the skip distance. 19.9, in the propagation diagram below, the area marked with the question mark, I think that's an error there. That should be the X, because we just did the question mark. They're asking for this area here. This is the skip zone, and we just did that a few questions ago. Now they're asking for this distance here, and that distance X is from the transmitter to where the skywave first returns to Earth, and that distance is known as the skip distance. You need to know the skip distance and the skip zone. 1920, the skip distance of a radio transmission is determined by the frequency used and the state of the ionosphere. 1921, the distance from a transmitter to the point where the signal first returns after refraction from the ionosphere is called the skip distance. 1922, skip distance is a measure of the, goodness me, long answers here, the distance from the end of the useful ground wave to the nearest point where the sky wave returns to Earth. Just happens to be the first one as the correct answer. 1923, a 21 megahertz signal will fade to a minimum at a point 400 kilometers away when two sky waves arrive out of phase. And I think this is our last one. As I said, there aren't a lot of questions on propagation in the standard, and there is a lot more to learn. So I would, encourage you, once you've done your standard, to maybe enrol in the Radio Electronic Skills Advanced course. 1924, the most reliable amateur band communications over a path of 160 kilometres during daytime hours is the 80 metre band. That's something you really just need to know. That 80 metres would be the band that you would choose. The others have too long a skip distance. They're much higher in frequency and their skip distance would be much longer than 160 kilometres. So you would use a lower frequency for a shorter skip distance to talk to someone via the ionosphere locally. Well, locally is 160 kilometres away. Well, that's it for propagation. Thanks again for your attention and listening to my droning voice. I'll see you back in the next tutorial. I hope you're doing well, and I really do hope you're enjoying this course. And please let me know how you're going. Even if you don't have a question, drop me an email at ron@res.net.au and just let me know how you're going. I'd like to know. Cheers for now. Catch you soon.